I'm Norbert Pelk. I'm Professor of Radiology Emeritus at Stanford University. As a graduate student, I did research in computed tomography and positron emission tomography. And then from 1978 to 1990, I worked at GE Medical Systems in all of the imaging modalities, but especially in CT, X-ray, and MRI. In 1990, I joined the faculty at Stanford and continued to do research in MRI, and then eventually, and for the last 2 decades, went back to my older interests in CT and X-ray, and that's what I've been working on since. Well, we in radiology have been using hot cathodes since their invention by Coolidge in 1917. They were a great advance compared to the previous Crookes tubes in that they allowed the tube to be controlled much more reliably than the older technology. But nonetheless, they have some significant drawbacks. Hot cathodes consume power, and even though the power consumption of a cathode may not be a big deal in a simple system with a single X-ray tube, if you scale it and have multiple X-ray tubes and all of them have to be on at the same time, the total power consumption of all the cathodes can become significant. So that's one of the drawbacks that the cold cathode could overcome. And, more importantly, at a given cathode temperature with a hot cathode, there's a coupling between the current, or MA, and the kV applied to the tube, so that the MA will vary with kV. And in particular, at low voltages, it may be difficult to get high current. And that would be another advantage that could be achieved by cold cathodes. A third issue with hot cathode is that depending on the complexity of the system, it may be hard to turn the tube on and off as quickly as we might like. And lastly, another potential advantage of cold cathodes is the distribution of X-ray emission over the focal spot, and the focal spot shape can be made more optimal than it is with hot cathodes. A lower cost X-ray source can allow us to produce X-ray systems of lower cost, and that's important, especially in settings where the customer is resource limited, for example, in the developing world. It's even more of an issue if we try to build systems with multiple X-ray tubes, because then the total cost of the X-ray sources in that system scales with the number of sources and can become a more significant issue. So the big advantage is that we might be able to produce systems that improve the healthcare of people throughout the world, but especially in resource-limited settings. We're really just now starting to scratch the surface, I think, in the topic of X-ray systems with multiple sources. One area where I think that they could have a big impact is in tomosynthesis systems. And in particular, tomosynthesis systems that would require simpler or perhaps no motion at all. I'm also enthusiastic about producing tomosynthesis systems that have broader and smoother blurring functions than are currently achieved, and also improved profile, improved response in the third dimension. High-end imaging systems at lower cost would be wonderful, especially if they could be coupled with easier and less expensive workflow. If you put those two things together, then the exam costs go down, healthcare costs would be reduced, and more importantly, the availability of imaging to patients would increase, and I think that would be a big win. I started working with the Nanox team as a consultant in 2012, so it's about 8 years now. Initially, I provided my opinions and advice in the impact on their technology on X-ray sources in general and in medical imaging in particular. More recently, about a year ago, I joined the Scientific Advisory Board of Nanox. As you can tell, I'm quite excited about the prospects for using the Nanox technology to build systems with multiple X-ray sources. I think that that will impact clinical applications and will benefit patients everywhere.
My name is Peter Dawson. I'm a professor of radiology in London, and I'm a member of the Nanox Advisory Board. My first training was in physics. I did a PhD in solid-state spectroscopy at King's College in London, and then I did postdoctoral work in Darmstadt in Germany. Subsequently, I trained in medicine and radiology and became Professor of Medical Imaging at the Royal Postgraduate Medical School in London. Latterly, I was Director of Radiology at the University College London Hospitals Group. My clinical interests and my research interests have always been pretty much the same: contrast-enhancing agents, cross-sectional imaging, and functional imaging. I've published widely in both physics and medical imaging. And now I think that I've clocked up no less than 35 years as a radiologist. In a conventional X-ray tube, the cathode is heated to more than 1,000 degrees centigrade. This boils off electrons. The process, of course, is called thermionic emission properly. These electrons are then accelerated to an anode and X-rays are produced. There are many problems with the system. One is sheer inefficiency. Only about 1% of the energy provided as electricity becomes X-rays. The rest is dissipated as heat. This has to be dealt with, and the tube has to be cooled in a number of ways. If you want to increase the intensity of the X-ray flux, you have to increase the intensity of the electron beam. The only way you can do that in these systems is to heat the cathode to a higher temperature. That, of course, is easily done, but it takes time. Not a long time, but there is a distinct delay. It's not a responsive system. These tubes also need rather sophisticated power supplies, and they need, as I said, lots of cooling. And when they're put in their containers with oil as part of the cooling system, they become very physically big, very heavy, and very expensive. The cold cathode tubes, a novel kind of tube, is entirely different. The cathode is cool, as the name suggests. It's at room temperature, in fact. You pull the electrons out instead of boiling them off, and you pull them out with an electric field. That's not as easy as it sounds. If you take a piece of metal and apply an electric field, you don't get a large flux of electrons. But nanotechnology has come to our rescue. If you form the cathode from a series of parallel, long, thin nanotubules, and then apply the electric field, then you get a large electron stream. And the reason for that is a little basic physics. If you apply an electric field near the tip of such a tube, the curvature of the tube at that point is very high, and the field gradient therefore becomes very high. And that's why you get the electrons. Importantly, these tubes are much smaller, much lighter, and much cheaper than the conventional X-ray tubes. Cost benefits of these systems will be considerable, and this of course will lead to benefits for patients by way of more accessible imaging. This applies both in the developed world and in the developing world. These systems could be placed in hospitals to augment or replace existing equipment, or they could be placed in standalone facilities covering a whole host of imaging requirements. In the developing world, it will certainly help to close the imaging gap. If you make a tomographic system, whether it be a conventional CT scanner or a tomosynthesis system, you have to move the X-ray tube. This is the only way you can get enough projections to collect enough data to reconstruct an image. In a CT scanner, for example, the movement is in a complete 360-degree turn around the patient. Now, to do this is no mean engineering achievement with a large, heavy tube. Nor is it cheap to build such technology. An alternative would be to put several X-ray tubes, I won't say as many as you like, but a number of X-ray tubes, on the arc in fixed positions. No rotation of the tubes or the arc, no moving parts at all. And the different X-ray tubes will provide their own projections without moving. Now, you can't do this practically with conventional X-ray tubes. They're big, they're heavy, and they're expensive. You can't start using lots of them and attaching them to your arc without running into all kinds of engineering difficulties. The new cold cathode tubes, you can. They're small, they're light, and they're cheap. So you can build an entirely different kind of tomographic system using. There is, of course, an imaging gap in the developed world. We can never provide enough imaging. Not only is it expensive, but populations are rising, demographics are changing, more older people in most of our populations are requiring more medical care and more supporting imaging technology. We have better informed, better educated populations who are demanding more. And of course we have doctors who are demanding more. They now understand perfectly the power of imaging. They understand how essential it is to everything they do, whether it be diagnosis, whether it be monitoring treatment, or whether it be intervention, which is occupying a bigger and bigger place in medicine. I've been a member of the Nanox advisory board for just about a year now. My role is to provide general clinical and general imaging input. The benefits of Nanox systems will be considerable. They'll be available at a lower cost, They'll therefore be more widely available, whether that be in the developed or the developing world. They can be installed readily in hospitals alongside existing equipment or replacing some existing equipment, or they can be placed in out-of-hospital facilities of various kinds. They could represent something of a revolution in imaging. I believe that the Nanox technology, with its potential versatility, with its cloud-based technology, and with its substantially reduced cost offer, is undoubtedly going to be very attractive to a lot of people. It could be, as I've said earlier, a game changer. I believe on the basis of this technology, Nanox has a very bright future, and I'm very happy to be working with them.
I am a medical physicist. I have been in this profession for about 25 years. It started at the Medical University of South Carolina. Now I have been at Duke University for about 20 years. I publish extensively in the field of X-ray imaging in general, computer tomography, radiography, tomosynthesis, and so on. I lead the clinical group at Duke University. This is the group that oversees the imaging physics operation in the Duke University health system. For most of its life, X-ray imaging has relied on X-ray tubes. X-ray tubes, you can think of them as a fancy light bulb. This technology has matured, is a very reliable technology, but it has some inherent limitations. The challenge is that you need to get the X-ray flux within a certain temporal time window and in a form that is as small as possible. So you can enable precise timing and precise spatial definition in the image that is formed. Cold cathode potentially provides us the opportunity to address both of those challenges, both in terms of timing, so you don't have to wait for the filament to heat up because you're starting with a cold source to generate the X-rays for you. So that addresses the timing problem. But also you can focus the X-ray beam much more finely, and therefore you can have finer spatial resolution in the images that you form. The challenge for us is to provide the same proficient, effective, precise technology at a lower cost. If we can do so, that would be a game changer. Diagnose the disease earlier. You can be much more precise in the diagnosis that you render, and therefore you can manage the patient more proficiently through the healthcare system. Most of the world doesn't have that privilege. We cannot provide that information, that technology to them because it's just simply too expensive. We have worked with them to try to create a simulation platform, a virtual rendition, if you will, of their multi-source technology to see what kind of advantages can be gained by such a technology, whether we will be able to see the disease perhaps more proficiently, more precisely, what would be the limitation of that technology. We already can generate three-dimensional images, beautiful three-dimensional images through computer tomography. The question is that can we also do that in a sort of projection space at a lower cost? The Nanox technology provides us an opportunity to move the source in two directions and therefore provide a more effective sampling of the spatial domain around the patient and therefore provide a more precise definition of the details within the body. I think that's a game changer.
My name is Jeff Rubin. I am a radiologist, a professor, and chair of the Department of Medical Imaging at the University of Arizona in Tucson. I began my career as a radiologist at Stanford University. After completing my residency and fellowship in body imaging there, I joined the faculty and was a professor for 17 years, developing applications for CT scanning and 3D imaging. In 2010, I headed east to Duke University, where I became the chair of the Department of Radiology. And then just recently, in the last month or so, I relocated again to Tucson, Arizona, to take on the role as chair of the Department of Medical Imaging there. The application of advanced technology in medicine really excites me. With the introduction of spiral CT, I had the opportunity to pursue the development of novel diagnostics in cardiovascular imaging, which is an approach that I have leveraged through my career into 3D visualization of vascular and non-vascular structures, as well as the application of machine learning and artificial intelligence to medical imaging data. The challenge of cold cathode tubes is that they require a level of technology that goes well beyond the traditional X-ray tube. In order to create a source that does not generate the level of heat of a traditional X-ray tube has required the development of a number of novel technologies. The benefits of a digital X-ray source relative to an analog X-ray source is the consistency and reliability of the quality of the X-ray beam. With a traditional source, variations can occur due to a number of different environmental conditions, age of the device. With a digital source, the ability to control the emission to a much greater extent and achieve consistency is realized. The cost benefits of a digital X-ray source is that an imaging system can be manufactured without the necessity of cooling the tube or other componentry that can really weigh down the system and add a lot of costs. It's a much leaner design with a digital system and therefore an overall lower cost system. The clinical benefits of a digital source are realized through the flexibility of design of the imaging system that is composed of those digital sources. There are really a spectrum of opportunities. The first is the design of low-cost systems and more portable systems that require less power and consequently can be delivered to low-resource regions of the world where it is a challenge to provide a consistent power source or even move heavy pieces of equipment in order to deliver the benefits of X-ray technology. The commercial introduction of a low-cost X-ray source is likely to have a substantial impact on the marketplace. I can't help but think about the old mainframe computers and the companies that were disrupted by new entrants with small portable devices. And the analogy is very much the same with the opportunity of digital X-ray sources. We will see a much broader spectrum of devices, much more diverse applicability for them, and price points that are much lower. There are unquestionably benefits to a multi-source X-ray system. We have seen that manifest in dual-source CT systems as they exist today, but we all know that those are amongst the most expensive imaging systems available, and no one dare consider adding 3 sources, 4 sources, or even more. By having substantially lower cost X-ray sources, the flexibility of multiple sources within a X-ray system provides for radically different designs that can substantially improve the quality of the images that we generate and the detail of the information that we derive. The benefit of a low-cost, high-end medical imaging system is that it will be much more widely available and in a much smaller form factor. Bringing medical imaging closer to the patient provides for opportunities for us to deliver the benefits of medical imaging more broadly within clinic rooms, within emergency departments, and assuring that as many people realize the benefits of medical imaging in their healthcare as possible. When medical imaging systems are available that cost tens of thousands of dollars, when previously they cost millions of dollars, the opportunity is to have those imaging systems much more widely available, to be able to be relatively unconstrained about their cost and site them where the patients are and bring imaging systems to the patients, whether they be in the back of an ambulance, whether they be in a clinic room or an emergency department. I've been working with the Nanox team for just over a year and have principally engaged with both developers and folks that are really concentrating on how to leverage this exciting new technology to bring benefit in the medical field. The benefits of the commercialization of a Nanox system are that it will be based in a digital, low-cost, low-profile X-ray source. And the flexibility of the system design resulting from a robust and reliable source will bring a wide spectrum of benefits to patient care. I think that the direction that Nanox is going is tremendously exciting, and that there has been a tremendous amount of interest by the public in seeing the tangible realization of these technologies in the clinical space immediately. I'd just like to say that we perhaps should be realistic when such groundbreaking technology is being developed to assure that it is fine-tuned and it is developed to be as effective as possible so that we're fully realizing the benefits in patient care.
Hello, my name is Dr. Michael Hughes. I'm a board-certified radiologist practicing for over 15 years. I'm a CEO of USRAD Holdings, and I'm a serial entrepreneur. Today, 2/3 of the world's population lacks access to even basic medical imaging technology. If we're able to take this technology and bring it to the masses, we'll be able to save many lives and decrease suffering. The technology that Nanox is manufacturing is at much lower costs, more mobile, more lightweight. And because of this, we're able to take this and bring us even to the remote areas of the world. It is important for all stakeholders to understand that Nanox is moving very fast, and it's still work in progress. They're still developing and improving what they already have built. I have been working with Nanox for over a year. Over this short period of time, I have seen a tremendous progress. A year ago, I was only able to see at two-dimensional X-ray images. Today, already we have a three-dimensional X-ray tomosynthesis.